Welcome to Programming in Modern C++. We are in week 2 and we are going to discuss module 6. In the last week, we have given an overview of C++ programming, particularly contrasting it with the programming styles in C or the availability of standard library in C and C++. And we have shown how, starting from very common simple programs involving IOs, variables, loops, to arrays, strings, sorting, searching, everything can become much easier, compact and much less error prone to write in C++, where often you need to write much less code and you get a much better quality of code. And from this, what I would strongly suggest is all the examples that were discussed in the last week in the 4 modules, first one being just the introduction. In the 4 modules, I would earnestly request you to try out those, executing those, build them on your system using whatever GCC you are using, and really check out what you are getting and make small changes and see how things are changing, so that slowly you start getting accustomed to the programming styles in C++. Now, from the module today, we are actually starting to get into C++ per se, its features, and primarily we will start focusing on certain features of C++ which actually make, I should say, it is a better C kind of a language. That is, these concepts were there in C, but C++ have found better ways of expressing them or handling them, so that it gets easier to use as well as better in the quality that you get. So, today in this module we are discussing about const-ness and inline functions, which are in contrast to 2 forms of macros that you had in C. This is outline as always. First, let us talk about const-ness and CV qualifier. So, in C, C++ both, we have manifest constants, or some people call it macros without parameter. So, we do that using hash define. So, we hash define this is a C preprocessor directive, and which takes the name and replaces it textually by the string that follows it till the next new line. Right. So, this is called hash define because you are defining a symbol, and if you want to understand a lot more about the C preprocessor, there is a separate tutorial also, you can go through that. So, here what we are primarily doing is we are defining 2 symbols, one is 2, which is defined as constant 2, another is pi, which is a constant expression. So, what does that mean? A tan basically means tan inverse. A tan is the name of the function, which is tan inverse. So, if you do a tan 1.0, that is tan inverse 1.0. So, we all know that tan pi by 4 is 1. So, tan inverse 1.0 is pi by 4. So, if you multiply this by 4, you get a value of pi. So, this is a convenient way to get the value of pi to a great precision. So, now what we do is we use these 2 manifest constants in the expression here to find the perimeter of a circle of radius r. Right. So, this is a manifest constant, and pi is a manifest constant as well, as these are also called macros. They look like variables. They look like variables, this is important, but they are not actually variables. So, what happens when the C preprocessor works? It takes every directive like the hash include, hash define and several others, and takes the action according to the directive. So, hash include includes the header files here. So, if you see the output after your pre-processing, you will not see hash include IOStream or hash include CMath lines, but you will see big code have come in which are replaced from the library files. Similarly, what it does for hash defines is it takes the definition of the symbol, fixed definition, constant definition of the symbol and replaces it wherever the symbol has occurred. So, 2 was occurring here. So, this CPP, the C preprocessor will replace 2 here. Pi is occurring here. So, it will take this text string of pi and put it here textually, right. And after it has done this, then it goes on to the compilation, right. So, compilation starts after the C preprocessor has worked. So, the basic problem is that the compiler does never get to know that there was something called 2 or something called pi, because compiler has not seen that, these are all gone. Compiler sees only this, which is a constant expression, and possibly the compiler will evaluate that constant expression at the compile time, because it can, and possibly what is left with is this kind of a number 6.28319, which is the approximate value of pi. So, that is where the basic problem of manifest constants lie, in the fact that they look like variables, but they do not behave like variables. Compilers never get to see them. Okay. So, that brings us to the notion of const-ness. The manifest constants, what are their purpose? Is to define a constant, right. And what is the purpose of a variable? Is to keep a value which can keep on changing, right. Now, we can combine these two in form of what is known as a constant variable, right, which is it is a variable in every respect, but after it has been created you cannot change its value. After it is created, after you have defined it, at the time of defining it you give it a value and then the value cannot change. If you think, hash define is exactly doing that, right. So, we do that using this notation. Int n initialized with 10 is a normal variable, put the keyword const before that, which means n will not be able to change. So, now if you want to make an assignment to n, there will be an error, there will be a compilation error, because compiler knows that value of n cannot change, it is a constant. So, in general we have we write this kind of code, right. Int is a m is an int, then star p is a pointer to an int which is initialized to 0. So, I can put the address of m in p, and using p in indirect way I can do star p assigned 7, which will actually change m, right. So, it is like this, I have m here which has something God knows what, then I have p here, I have put ampersand m here. So, p points here, and I do star p assigned 7. So, this becomes 7. So, I have not even talked about m, but I can change the value of m. This is a common program. Can I do this? Can I have p and make it point to n, which is 10 const? Can I do this? If I could do this, then I could have done say star p assigned 5, and that will change this to 5. Then the basic property that n is constant will get destroyed. So, I cannot do this. So, I say that p, while p is a pointer to an integer, ampersand n, the address of n, is actually a pointer to a constant integer. That is a different concept. So, being a pointer to an integer and being a pointer to a constant integer are different, right. So, we will see little more of that soon. So, naturally a constant variable must be initialized when defined, because otherwise you cannot change them, and variable of any data type can be a constant. So, we have given an example of the complex number variable. So, here you can see that I am saying this is const and initialized it. So, which respectively initializes the two components, but then if I want to change any component separately, I will get a compilation error because C is a const. No component can be changed. That is the basic idea of const-ness. So, now let us try to use this. This was my manifest constant or macro style of definitions. Now, I have it in terms of const. So, now the C preprocessor does not replace 2 and pi, because they are no more hash defined. They are no more manifest constants, they are just variables. So, the compiler gets to see them, compiler gets to know their type, and the compiler can take lot of decisions based on what their type and the value is. So, that is the basic advantage of having const in the system. So, basic advantages: one set of const values are basically naturally constant numbers like pi, e, golden ratio and so on and so forth. Whereas, remember that what we use as NULL capital in C or C++ is actually not a const value, it is actually a manifest constant. And then the other value of the constant is to define program constants. There are several things like maximum size of an array, number of elements, number of people. If there are these are constant values, then you can always put them on the top or in some header together and define them only once, and make sure that all through the program they cannot be changed even inadvertently, because we have made them const. So, it makes the programming much safer, much easier to do. Okay. So, we would always prefer const over hash define. Okay. So, these are some of the reasons that manifest constant does not have a type, whereas constant variable has a type. So, it is type safe. Manifest constant is textually replaced by CPP. So, you do not get to actually see, if you have a number of manifest constants and expressions involving them, then you do not get to see as to what is the result of this replacement, right. Compiler, what the compiler sees you do not get to see, and what you see is what the compiler does not see. But if you use as a constant variable, both of you see the same thing. Since manifest constants are replaced by the preprocessor, they cannot be watched in the debugger. You cannot see what is the value of n in the debugger if n is manifest constant, whereas if it is const int, you can see it in the debugger. And also the manifest constant, like the pi expression we saw, they are replaced, wherever they are replaced they are evaluated. Whereas, if you have a constant variable, then naturally its evaluation happen only at the definition time. Everywhere else you just use that value. So, it is also efficient. So, in every possible way manifest constant are a no. Stop using manifest constant, just use constant variables. Now, let us quickly look at constants and their interplay with the pointer. See, how would const-ness apply to the pointer scenario? So, suppose I have a, like I have here, I have n here, I have p here, n is has a value 5 and I have p as a pointer to n. So, this is the structure. Now, the question is, if I want to talk about constness, what is const? Is this const, that is I cannot change the value it is pointing to, or is this const that I cannot change this pointer, that is I cannot make it point to something else. Okay. So, there are two notions of constness. One is pointed to constant data, that is if p points to something which cannot be changed, then it is a pointer to a constant data. This is constant. Whereas, if p is a constant pointer, then it cannot be changed to point to anything else, cannot be done. It becomes a constant pointer, right. Two types of constness, and actually you can have both at the same time as well. Right. So, here are the examples. So, you see pointed to constant data. So, you have a constant variable here, and you have a star p which points to a constant data. Right. So, you can use this. Now, naturally you cannot assign to n because it is constant, you cannot assign to star p because if p is pointing to a const int, then star p is constant. So, the fact that you will use p to change n is not possible, right. You get this safe, whereas p can point to some other m which is not a constant, and you can change m accordingly. Right. So, we can have this kind of situations as well. Now, we can also say we have a constant here, and suppose I want to use that address to initialize int star p. That also is an error. Why? Because int star p tells me that star p is int, it is not constant. So, if I am allowed to put the address of const int into p, then when I do star p and change it, I will not be able to know that I am changing something which I am not supposed to change. So, this itself is an error. So, that is how the logic of that is the way to look at the logic of constness. So, here you can see that I am talking about another type of constness, that is I am saying in star const p, which is a constant pointer to a non-constant data. So, as n is not a constant, I can put a value. I can do star p is int, star p is int. So, it is changeable. I can assign 7 to it. So, by which n will change to 7, that is okay. But I cannot do this. I cannot make p point to a different variable m, because the pointer itself is constant. So, earlier we saw the pointed data point is constant, here we see that the pointer is constant. Right. So, it depends on which side of the star you write the const. Right. So, if we look in here, then we can certainly have const on both sides, which says that it is a constant pointer to a constant data, that is using p. Neither I can change n because it is a constant, it is pointing to a constant data, nor can I assign any other address to p because it is a constant pointer. Right. So, that is the basic types of constness with pointer. Now, you may from the syntax you may get confused at times. So, for example, I would just tell you how to get confused. For example, say I am writing const int star p. Into something. This is a pointer to a constant data. I am writing int const star p. This also is valid, and it also means pointer to a constant data. I write int star const p. Now, it is not pointed to a constant data, it is a constant pointed to non-constant data. Confusing between these two, right? So, it is a very simple rule. Whenever you have to write or when you see the code, just draw a vertical line through the star. Whichever side the const is, that side is const. So, if you draw it here, it is on the pointy side, the pointy is const. You draw it here, it is also on the pointy side, the pointy is called. If you draw it here, it is on the pointed side, so pointer is const. You draw it here, it is on both sides, so both are const. That is a simple way to resolve, right. Otherwise, it gets quite confusing at times. So, here is an example of using const with C string. You can see that I can have a string created and I can access an element and change it. I can copy another string into this name, that is I can change an element or I can change the name altogether. So, NIT Kharagpur, JIT Kharagpur. Now, if I put a const here, that is if I make the elements constant, star is here, so pointy elements are constant. So, if I make those constant, then naturally I cannot change them, I cannot edit. This becomes a compilation error. If I put it on this side, that is if I put it on the pointer side, then I can change the element, change the name, but I cannot change the name. And if I put it on both, I cannot change either. So, it depends on what is that I want, and accordingly I can do these changes. So, there is another concept related to this, it is called CV qualifier. C is for constant, V is for volatile. So, we have talked about constant where you initialize and cannot be changed. Volatile is a very peculiar concept where you say that a variable is volatile if its value can change even without an assignment. Normally what we know that you have to do a write for the value to change. But if I have a variable whose value can change by itself automatically, then it is called a volatile variable. Volatile variables can happen because of several things. For example, I may have modeled a port, IO port as a variable. When the data is written to that port, naturally then the variable value has changed. A different data is written to the port, the value of variable has changed, and I do not know what value the hardware is going to write to that port, right. So, without me knowing, the value of the variable can change. This can happen because of kernel writing something, this can happen because of some other thread writing a variable. So, such variables are typically can be marked as a volatile, because it does help in a significant way for the compiler. So, just see here I is assigned 0 and I have this loop. Right. Now, you obviously can know that since no changes to I are being made, this loop is going to be an infinite one. I is not equal to 100 and will never become 100, this is an infinite loop. So, what the compiler will do, it will optimize and say that this can never be, this is always true. So, it will make it 1, right, this optimization. Now, suppose you change that, instead of static int I, you just make it static volatile int I. So, you are saying that I can change by itself. Now, the compiler will not be able to optimize, because it does not know if somebody at some point of time can change the value of I and make it 100. If it does, then the loop will exit. So, being volatile, I can be changed by the hardware or by other thread at any point of time. So, it helps. It is not a very frequent use, but this is the other kind of qualifier besides the const, which has the other extreme of the meaning, is what is useful in terms of the qualified variable values. Next, we will talk briefly about inline functions. Inline functions are like, we have macros. So far we talked about manifest constants, which are macros without parameter, but these are macros with parameter. So, this is like, again, they are hash defined. So, they have a parameter and then expression. So, when I invoke, I say square a, they are textually replaced, and you actually get in preprocessor expansion, you will get this replaced by a star a, which is a very simple concept and very useful for having compact computations done. I could have done a function also, but function has a lot more of overhead to write this multiplication beyond this multiplications, which is just here in place. So, it gets a lot more efficient to do. Now, there are several pitfalls, and I am sure many of you would know about these, that what if I define the macro like this and call it by a plus 1. Now, I would expect that if a is 3, then a plus 1 is 4. So, mentally I am thinking that this is a function. So, I expect a square, I want 16, but if you do this, you will get a result 7. Why? Because this is textually replaced by the C preprocessor. So, what it will replace is a plus 1 star a plus 1. So, now this becomes the priority operation. So, it becomes a plus 1, which is 3 plus 3 plus 1 is 6 plus 1 is 7 is what you get. Well, you can get rid of this by putting parentheses around them. Then it will be like this, and this is what you must have read in different books also, that by doing this you will make the macro safe, right. Great. So, let us try to be the devil a little bit more. I have the same, now I have the corrected macro, and I invoke it by plus plus a. What I expect? 3 plus plus a is 4. So, I will get 16, but try this, you will get 25, because you get this as a replacement code. So, instead of 1 plus plus, there are 2 plus pluses, 2 pre increments. So, 3 gets 4, 4 gets 5, and then 5 gets multiplied by 5 gets 25, and it is not easy to fix by writing a macro in this way. So, macros are good, but they are an evil. So, what C++ does, it defines the concept of a inline function. It's extremely simple. It's just like any other function, just you write inline, the keyword inline in front of it. So, instead of writing this, you just write this, which is a function. So, since it's a function, the system will first evaluate the actual parameter and then make a call to it, right. So, if we do this, then here with this will fail, this will fail, there is no type check, but here everything will work fine because it is a function. And because it is inline, it actually is not making the function call. The compiler does a trick so that the function is embedded right here, but with all the type checks and with all function protocols like evaluate your actual parameter and then pass it to formal parameter, not just do a textual replacement and so on. So, the semantics of function remains, but the efficiency of macro is obtained. It is a win-win situation. So, that is the basic idea of the inline function. So, you should stop using macros and only use inline functions. Here it is a simple comparison of that. In the first 3 points are same between the two, the code bloats and all that, but macro has significant syntactic and semantic pitfall, which Inline does not have type checking is available in Inline, and it helps to write max swap for all types, which obviously cannot be done by inline function, and we will see a different solution for that. Right? You can, and one way you write a swap function using a macro, because you need it to work for any type of data. But we have already seen, and we can handle those situations using that template and meta programming. Otherwise, everything else in terms of inline functions are a plus, and we would always use inline functions only instead of macros. Now, of course, inline also is, you should keep in mind that it is a directive. So, just because you write inline, it may or may not be inlined, because the compiler makes a judgment as to whether it is more efficient to inline or it is more efficient to not inline, outline the function, so to say. So, it's a compiler directive. Compiler makes a judgment on that, and always implement the inline functions on the header, so that you do not have two different definitions of the inline functions. Do not implement inline functions in the source file, which is otherwise, because the compiler needs to know the code when the function is called. Just knowing the signature will not work. Right? Okay, so to summarize, we have looked at the two very basic extensions of C into C++, that is a const-ness and inline function, which can do away with all kinds of macros without and with parameter. Thank you very much for your attention, and we will meet in the next module.